I welcome you all to the next exciting class of Expert 360. Today, I will be just going for the review of Laplace transform. See, today's class, I am taking Laplace transform is just to teach you network analysis, because in network analysis, mostly you need this Laplace transform. That is transient conditions and all, and the two-port networks, all those things. When you solve it, you will need the Laplace transform. So the second subject is control system. When I teach you control systems, I need again this one, control systems. Then the third subject, when I teach you signals and systems, all the mostly electrical and electronic students, all the students have to study signals and systems. In that portion also, I need Laplace transform. So before going into those subjects, I like to teach you the review of, I go to the review of the Laplace transform, just the basic things what you need over there. Okay, these Laplace transform you have all studied in the first year. Engineering first year students have studied this Laplace transform. And the application of this, I'll going into the, when I go into the second and third year subjects of network analysis, signals and systems, control systems, analog electronic circuits. When I am using high frequency analysis, I need these Laplace transforms. Okay. So now I've just given you the definition of it. The Laplace transform, you usually put as L of f of t, which is equal to integral 0 to infinity e raised to minus f t f of t dt, which I will usually denote as capital F. For all t greater than 0, so I put the integral from 0 to infinity, t is greater than or equal to 0, and s is a parameter which is real or complex values. Okay. So what I am going to do with this Laplace transform? Let us see that. Whenever I have an equation, when I have a sinusoidal waveform, it is sine omega t. Such things will be there, sine omega t. I need these things to transfer into frequency domain. This is in time domain. So any signals in time domain, I have to transfer into frequency domain. It is a continuous signal. See, it is a continuous signal in time domain. I am transferring into frequency domain. Then this time domain, this continuous time domain function, I will put into S domain, that is Laplace transform, then put S is equal to j omega, it goes into the frequency domain. So j omega, that is a complex value, that's what the thing is complex. Okay, put S is equal to j omega. Then if it is not continuous, you have discrete systems, then you will go for Z transform. Instead of Laplace transform, you will go into Z transform, and you will be putting Z is equal to e raised to j omega, which will go into the transform frequency domain. Okay, then you will be having in that when you study digital signal processing, you will be studying all those things, the transforms and all you will be studying. Okay, so Laplace transform, why am I using it? I am just want to transfer the time domain function into frequency domain function. For that, this time domain function, first of all, I will bring it to S domain and then put S is equal to j omega, which transfers this into frequency domain. See, some formulas, you all know these formulas. Still I have given you the Laplace of 1, that is equal to 1 by S. Laplace of e raised to at, 1 divided by S minus a. Laplace of e raised to n, which is the n factorial divided by s raised to n plus 1. Laplace of sine at, a divided by s square plus a square, where s is greater than 0. Laplace of cos at, which is equal to s divided by s square plus a square, s greater than 0. Then sine hyperbolic function, sine x at. You can also write that s sine x at as something like this. You can have like this also, sine x at can be written as e raised to at minus e raised to minus at divided by 2. Similarly, cos x at, you can put as e raised to at plus e raised to minus at the whole divided by 2. This is another formula for sine x at. Okay, so sine x at is equal to a divided by square minus a square, s greater than modulus of a, hyperbolic function. Laplace of cos h at s divided by s square minus a square, yes, modulus of s greater than modulus of. This is the formula for sine h at. You can have the Laplace transform of e raised to at minus e raised to minus at divided by 2. Instead of sine h at, you can put it over here. This one you can put it over here. The same answer you will be getting. this one, you can put it over here, you'll be getting the same answer. These are things I need in the circuits for simplifications. That's why I told now is sin x 80 what it comes, cos x 80 what it comes. Okay. Now let us come to the first shifting theorem. If Laplace of f of t is equal to capital F of s, then Laplace of e raised to at in f of t is equal to f of s minus a. That is, suppose the Laplace of sin 80, you know what is the Laplace of sin 80? It is a divided by s plus s square plus a square, a divided by s square plus a square. Okay. Laplace of sin bt, b divided by Laplace of sin bt. Okay, sin bt. What is that? B divided by s square plus b square. Then Laplace of what the first shifting theorem says that if e raised to at sin bt, I just multiplied this by e raised to at, then this becomes all the s has to be replaced by s minus a. All the s has to be replaced by s minus a. So this becomes b divided by s minus a the whole square plus b square. Clear? This is the thing. What is coming out? Okay. Now multiplication by t raised to n. If Laplace of f of t is equal to capital F of s, then Laplace of t raised to n and f of t is equal to minus 1 the whole raised to n dn of f of s divided by dsn, where n is equal to 1, 2, 3, etc. This is also important. So you may have t into sin 80, t into sin. So sin 80 you will have to find the Laplace transform of sin 80. Then t into, that means it is t raised to 1. So you will have to differentiate once. Okay. When we come to the problems, you will be knowing that how to do it. Anyway, most of the students have studied that, all those things. Division by t. So if Laplace of f of t is equal to capital F of s, then Laplace of f of t by t will be, that is division by t, which is equal to integral s to infinity f of s ds. S to infinity f of s ds. Then Laplace of unit step function. This is very important when you do signals and systems, network analysis, in all those, control system, all those, you need this one, unit step functions. So Laplace of u of t minus a is equal to e raised to minus as divided by s. That means Laplace of u of t, that means a is equal to 0. Laplace of u of t. Let us go for Laplace of u of t. Laplace of u of t, that is equal to a is equal to 0, right? A is equal to 0. So Laplace of u of t is equal to e raised to 0. Yes, that is e raised to 0. That is 1. So that is equal to 1 divided by s. Clear? Laplace of u of t. That is the unit step functions. Okay. For unit step functions, you will be having Laplace of u of t is equal to 1 divided by s. Next. See, suppose what is this unit step function means? Let us go for that. What is mean by unit step function? It is something like this. See, this is what unit step function means. This is x of t or f of t, and this is t. So this is 1. That is unit step function. You will be having a constant value after 0. Suppose you have this is a, then you can put it as this is 10 volt, 20 volt, something like that, a volt. So then you can put 10 volt, then you can put it as 10 u of t. Here it will be a u of t. Then what is the Laplace of this? 10 u of t, that is equal to 10 divided by s. And this is equal to a divided by s. This is how you do the unit step function, the Laplace transforms. Okay, when you are applying a voltage of 10 volt, a step voltage of 10 volt, at that time you will be using these values. Okay, suppose it is u of t minus a. What does it mean? U of t minus a, the shifting. That is all you study in the signals and systems, the shifting formulas, shifting, how to shift the waveforms. That is, you will be starting like this. This is u of t. I will be teaching over there in the signals and systems. You don't get worried. This is thing. This is u of t. Suppose I need u of t minus a. This is the a, t minus. So I have to go to the front, t minus a. So this is t minus a. Okay. So this is the thing, u of t minus a. This is equal to 1. Okay. This is equal to 1. So these are the sequence you have in the sequence and systems. You will be studying it, and network analysis also you need this. So that is Laplace of unit step function. Laplace of u of t minus a is equal to e raised to minus as divided by s. That is important. Now I'll go into the other step functions and all. So you see, next one is Laplace of f of t minus a u of t minus e is equal to e raised to minus as into f of s. See, I've written that. What is that f of t minus a to u of t a minus means? So that is for f of t minus a for t less than a, t minus a. So t less than a, the value is 0, and for t greater than a, the function it comes as f of t minus a. So the Laplace of that will be e raised to minus as into f of s. Okay, suppose you just see, that is what, if a is equal to 0, a is equal to 0, here also it is 0, so it is f of t into u of t, f of t into u of t, that is u raised to 0, that is what you will get, f of u raised to 0 is 1, so it is f of s. So f of t into u of t, it is a f of t is a function, unit step function, then it will be having it as f of s. Okay, now unit impulse function. Impulse function, what is impulse function means? See, this is del of t, del of t. This is a signal only just on impulse at 0, at the origin. Suppose it's t minus a, where should it go? It should shift to the right hand side. So this is t minus a, this is t minus a, this part will be a, this is equal to 1. Okay, t plus a means it has to shift this side. That is del of t minus a. So it is del of t minus a. It is 1 by k. It is given as 1 by k. So this is 1 by k. The height is 1 by k. It is not equal to 1. It is 1 by k. For a less than t less than a plus k, which is equal to 0 otherwise. And Laplace of that is equal to e raised to minus as. And if it is del of t, then it becomes e raised to 0. Then it is 1. So Laplace of an impulse function del of t, that is equal to 1. Del of t is equal to 1, and del of t minus a means it is simply just e raised to minus a. And the next one is very important, the periodic functions. Periodic function. When you study in Laplace transform in mathematics also, you usually get one question in this periodic functions. Okay, so periodic function. A function is said to be periodic. You know it, what it is, with a period t, that is f of t plus capital T. After a time period of capital T is going to get repeated. It is equal to f of t. For all t greater than or equal to 0, the Laplace of periodic function is 1 divided by 1 minus e raised to minus st integral 0 to t e raised to minus st f of t dt for s greater than 0. These are the some important formulas which you have to study while studying Laplace transform. Now I come to inverse Laplace transform. Again, that is more important in inverse Laplace transforms. Okay. So now we will come into inverse Laplace transform. Okay, inverse Laplace transform. You have, if Laplace of f of t is equal to capital F of s, then the inverse of it, you are bringing this to here, that is Laplace inverse. Okay, Laplace inverse of f of s, that is equal to f of t. I have given the formulas. So Laplace inverse of 1 by s is equal to 1. Laplace inverse of 1 divided by s raised to n, that is equal to t raised to n divided by n minus 1 factorial. Laplace inverse of 1 divided by s minus a, and Laplace inverse of 1 divided by s plus a. This is e raised to 80 and this is e raised to minus 80. This usually we come across in signals and systems. Laplace inverse of 1 divided by s square plus a square sin 80 by a. Laplace inverse of s divided by s square plus a square, that is equal to cos 80. Laplace inverse of 1 divided by s square minus a square, that is sin h 80. Sin h 80 you can write as e raised to 80 minus e raised to minus 80 divided by 2. And Laplace inverse of 1 divided by s square plus a square, that is cos h 80. See the first shifting theorem, just the inverse of it. Laplace inverse of f of s minus a, you can put it as e raised to 80 into Laplace inverse of f of s. That is, sometimes we may have the functions like this, that is something like s minus 2 divided by s minus 2 the whole square plus phi square, something like this. See, if the 2 moves off, the formula is what? S divided by s square plus phi square. So if the 2 is not present over there, then what the formula is? It is s divided by s square plus phi square. What is that? Laplace inverse of that is what? S divided by s square plus y square. That is, see, it is cos 80. Laplace inverse of s divided by s square plus a square. So this has been, all the s has been replaced by s minus 2. Right? All the s has been replaced by s minus 2. That is what it means over here. That is, all the s has to be replaced by s minus a. Here it is s minus 2. Okay, that is, suppose it was cos 80, it would have been s divided by s square plus a square. Suppose e raised to bt into cos 80, that means all the s will be replaced by s minus b. Okay, similarly, that means this 2 has to go off. So that means what is the formula comes? It is e raised to at, e raised to 2t. This is a. So it is e raised to 2t into Laplace inverse of, this 2 has gone off, Laplace inverse of s divided 2 is not there. Okay, what is this? E raised to 2t, Laplace inverse of this is cos phi t. Clear? This is the thing. This one, first shifting here. Then you have the multiplication, just the inverse of it, that is t f of t, that is equal to Laplace inverse of minus d by ds of Laplace of f of t. Then f of t by t, that is equal to Laplace inverse of integral s to infinity Laplace of f of t ds. Okay, now we will come to convolution theorem. That is again important thing about is convolution theorem. Okay, come to convolution theorem. The Laplace convolution of f and g is denoted by f star mark of g and is defined as integral 0 to t f of u g of t minus u du. If Laplace inverse of capital F of s is equal to f of t, that is, suppose I have, it is f of t, that is equal to, I take my f of t as 1 divided by s plus 2, and Laplace inverse of g of s is equal to j of t. Okay, this is 1 divided by s square. Then Laplace inverse of f of s into g of s is equal to integral 0 to t f of u g of t minus u du, or that is also equal to integral 0 to t g of u f of t minus u du, which means that f star mark of g is equal to g star mark of f. Okay, so you have something like this. You have to find the Laplace inverse of this one. You can use convolution theorem over here. This is 1 divided by s plus 2 into s square plus 25. You can take this term, that is 1 divided by s plus 2 as f of s, and the g of s as this one 1 divided by s square plus 25. You can take the either manner. If you want this as g of s, you can take this as g of s and this as f of s. No problems. We can just interchange that. And you can find, using that formula, you can write as integral 0 to t f of u g of t minus u du. That is, f of u means you will have to find the Laplace inverse of this one, f1 divided by s plus 2. You know that it is e raised to minus 2t, e raised to minus 2, and g of t, g of s, we are taking this as, then this will be what? S square plus phi square, s square plus a square, 1 divided by s square plus a square, that is what? 1 by a sine 80. So this is 1 by phi sine phi t, 1 by phi sine phi t. So actually you can put it in the form integral 0 to t f of u, that is e raised to minus 2t into this one g of t minus u du. So this one will have a sine phi, 1 by phi sine phi t. You can put the formulas over here, f of u g of t minus u du, and you can find it. Okay, we will get these type of problems while doing signals and systems. You have the convolution theorems which has to be applied. There you will be have to do this. Okay, this convolution theorem, and I think Laplace transform, Laplace and inverse Laplace transform, I have just gone through. Again, when I do the problems in signals and systems or network analysis or in control systems, all these subjects, when I go through, if there is any other things which has to be taught, I will teach you at that time. Okay, no problems in that. Anyway, this much portions you should know it. You should remember all these things when you come into that subject. Okay, and that's all the things we need. Okay, fine.